In this video, I'm going to give you a beginner-friendly introduction to symbolic logic. This area of logic was developed in large part by George Boole, an English mathematician whose work became the foundation of Boolean algebra. Symbolic logic is behind many things in computer science, like how databases work, how computers make decisions in AI, and how digital circuits are designed. We'll start by looking at logical form. Let's start by looking at a specific type of deductive reasoning called an argument form. Here's an example. You are either interested in computer science or you hate yourself. You hate yourself, therefore you are watching my video. This is an example of an argument form. An argument form leads to a conclusion, a statement that is either true or false. The conclusion is based on one or more premises. There are statements that come before it. The premises must be acceptable on their own, either because they're clearly true or because they follow from other known truths. Here's another example, one that even my innie wouldn't notice. I will go to work either today or tomorrow. Tomorrow is a holiday. Therefore, I will go to work today. The conclusion is, I will go to work today. Seems airtight, right? No way around it. But would I actually go to work today? Maybe not. Maybe I'm still haunted by that hasty GitHub commit from last week. The one that screamed slop vibe. And I can't just face the code reviewers. That would make the conclusion false. But more importantly, if I didn't go to work today or tomorrow, then the first statement, the premise, would also be false. So yeah, you're not just hallucinating logic here, folks. The structure matters. If both premises are true, then our conclusion is also true. Both the arguments we've used are valid. Let's create an example of a deductively invalid argument. Take a look at this argument. Either Jan or Ilya is wrong. Either Ilya or Sam is wrong. Therefore, either Jan or Sam is wrong. Now, let's suppose Ilya is wrong, but both Jan and Sam are actually right. The first premise, either Jan or Ilya is wrong, is true because Ilya is wrong. The second premise, either Ilya or Sam is wrong, is also true. Again, thanks to Ilya. But the conclusion, either Jan or Sam is wrong, is false, since both of them are right. So what's the problem? Even though both premises are true, the conclusion doesn't logically follow. That makes the argument invalid. It's a structural issue, not a content one. Also, sorry Ilya, you're the fall guy again. You always are. What is a statement? I think it's time to define things a bit more precisely so your understanding isn't as vague as when I vibe code my way through a project. Let's start with the definition of a statement. A statement, sometimes called a proposition, is a sentence that can either be true or false, but not both. That's it. No shredding a sentence here. Here are some examples of statements. 1 plus 1 equals 2. Yeah, try telling that to a postmodernist. 1 plus 1 equals 3. Also a statement, but this time it's false. A proper statement can't be ambiguous. If I say he is a programmer, we've got a problem. The pronoun he doesn't point to anyone specific. In logical terms, it's like using a free variable with no assigned domain. He could be anyone, a vibe coder, an art school reject, pivoting into destruction, or just some guy who thinks adding semicolons to Python makes it faster. Unless he refers to a clearly defined individual, we can't say whether the statement is true or false. It's not a valid proposition. It's just a sentence wandering around the syntax wasteland, hoping someone gives it a meaning. Let's take a look at the following example. If I had pulled the latest changes or resolved the merged conflicts properly, then the repo wouldn't have turned into a spaghetti timeline. But now we are in commit purgatory. This is a valid argument, not because of the get pain, but because of its logical form. Let's assign some symbols. P equals I pulled the latest changes. Q equals I resolved the merged conflicts. R equals the repo didn't turn into a spaghetti timeline. So we have if P or Q, then R. Therefore, not P and not Q. This works because of two key ideas, the contrapositive and De Morgan's law. but we'll talk more about that in another video. So yes, the repo is doomed, but the logic is sound. From here on, I'll use symbols like P, Q, and R to represent statements. Keep the following in mind. We'll be building compound statements using logical connectives. Here are the first few connectives. Or, also called a disjunction, and also called a conjunction, and not, also called a negation. So say we have two statements, P and Q, that's statements that we have separately. This means P or Q, which is the disjunction, that's also a statement. This means P and Q, which is the conjunction, that is also a statement. This means not P, which is a negation, is also a statement. Now about the order of operations. Because yes, logic has rules too, parenthesis comes first, just like in regular math. And or are considered equal in precedence and are evaluated left to right. Negation is applied directly to a statement. It comes before conjunctions or disjunctions, but after parentheses. Negation must always be attached to a specific statement. It can't just float around there by itself like a dramatic pause. Also, some English words don't translate directly, but we can map them to logic. For example, but is usually just and in disguise. Neither P nor Q translates to this. In other words, both are false, because natural language is messy, but logic likes things tidy. Can you write the following statements in symbolic logic? Share your answers in the comments below, and yes, I'll be judging you silently, but logically. Either I fix a bug, or I rewrite the entire code base in Rust. I tested it in production and I regret everything. The bug is not reproducible. Neither will I ever write kernel code in Rust, nor will I like Brendan Ike. Sorry Brendan, JavaScript is still painful. This was a light video to kick off our journey into the weirdly structured, sometimes cursed, but undeniably beautiful world of computer science and logic.
That's weird.
If you had fun, learned something, or at least felt mildly attacked by one of the examples, go ahead and subscribe. Next time we'll dig a little deeper. But don't worry, I promise to keep the existential dread logically consistent.